Welcome to the quotient rule. So previously in this section, we've seen how to take the derivative of a product of two functions. And now we want to see how to take the derivative if quotients are involved. So we have now seen how to take the derivative if sums, differences, or products are involved. So next up is what about if there are quotients? So the quotient rule, what we are doing is we wish to take the derivative of a function f of x over g of x. And if we take this derivative, what we wind up getting is we do the derivative of the first f prime of x times the second g of x. Then we subtract the first times the derivative of the second g prime of x. And then we divide that whole thing by the denominator g of x squared. So again, we have the derivative of the first times the second minus the first times the derivative of the second all over the second squared. So let's go ahead and just take a look at a couple of examples. So first up, let's find the derivative of f of x equals 3x squared divided by sine of x. So we know that f prime of x is equal to, we have a quotient, so we're going to have a big fraction bar. We do the derivative of the first. So the derivative of our 3x squared times the second times sine of x. Then we subtract the first 3x squared times the derivative of the second. So the derivative of sine of x. All over the denominator sine of x. The whole thing squared. So again, the rule, we do the first derivative of the first times the second. And we do the subtract the first times the derivative of the second. And then we divide by the second squared. So from here, we have f prime of x is equal to, well, the derivative of 3x squared using the power rule. We would have 3 times 2x and then times sine of x. Then we would subtract off 3x squared. Derivative of sine of x is cosine of x. And then we divide that entire thing by sine squared of x. I'm doing one last stage of simplification. This becomes 6x times sine of x minus 3x squared cosine x. all divided by sine squared of x. So this is again using the quotient rule to take the derivative. So we have one more example. Let's go ahead and find the derivative of g of x equals e to the x plus 1 all over x squared plus 4x. So I'm going to color code once again. So my first is highlighted in yellow. My second is highlighted in green. So we have g prime of x is equal to, the quotient rule says, we do the derivative of the first times the second then we subtract the first times the derivative of the second. And then we divide by the second squared. So we have the derivative of e to the x plus 1 times x squared plus 4x. And we are subtracting off e to the x plus 1, our first, times the derivative of x squared plus 4x. And then that is all over x squared plus 4x, the whole thing squared. At this point, the derivative of e to the x plus 1, well, the derivative of e to the x is simply e to the x. The derivative of 1 is 0. Then we multiply by x squared plus 4x. Then we are subtracting off. We have e to the x plus 1. The derivative of x squared plus 4x, so the derivative of x squared, power rule says that's 2x. Derivative of 4x, we're just looking at plus 4, all over x squared plus 4x, the whole thing squared. At this point, we could go ahead and multiply out, rearrange, combine like terms. If we simplify that numerator, we have an x squared e to the x plus 4x e to the x. Then we have a bit of FOIL going on. We have minus 2x e to the x minus 4 e to the x minus 2x minus 4. If we multiply out that last term, all over x squared plus 4x, the whole thing squared. And then our only like terms are, we have x squared e to the x plus 4x e to the x minus 2x e to the x. We wind up with a plus 2x e to the x. Then we have minus 4 e to the x minus 2x minus 4. And I'm just going to leave my denominator as x squared plus 4x, the whole thing squared. So again, this is using the quotient rule. That's a little uglier than the product rule, just because we have some extra components to it. We also this time around had more addition and subtraction involved, whereas our product rule examples were a little simpler. But this is sort of the gist of the quotient